free to start whenever you're ready.
Thank you very much. Thanks a lot for the invitation. It's my great pleasure to be here today. So yes, title, let's go for it. So I'm going to talk about algebra objects in something called group theoretical fusion categories. Let me first point out that this is joint work with Gibi Morales from the University of Los Andes in Bogota, Monique Müller from São João do Rei in Brazil, Julia Plavnik from the Indiana University at Bloomington, Angela Tavir, who is currently at Ames, Ghana, and Chelsea Walton right now at Rice University. So this talk is going to be based on this archive preprint that actually we submitted not so long ago. And this collaboration started thanks to the winner, the Women in Representation Theory 2 workshop. So I'm super proud of this. I'm going to mention it. As the title suggests, the main character of today's talk are going to be algebra objects in tensor categories, or categories with a tensor product. So these guys appear in many, to me, cool research projects. Research problems. Let's say the first time I encountered them, it was in the study of boundary conditions in full rational CFT in this series of papers by Fuchs, Hunke, and Schweiger, and also collaborators. But also it seems to appear, this notion of VOA, related to this notion of VOA extensions, which were developed by Huang, Kirillov, and Lepowski, and extended to super case by Kreutzig, Kanade, and McRae. Happy to have you on board, guys, today. But actually, they also appear in the study of something called R-spin topological field theories. This was developed by Novak and Hunke and Siketi, so my PhD advisor and two of my PhD brothers. And actually to come up with new examples of these topological field theories amounts to find algebra objects in a certain tensor category one can associate to this TFT. So actually, as maybe you can, at least to me, they're very interesting mathematical objects, but sometimes they're tricky to find. So, okay, quite a question. Actually, I would like to, because most of the speakers have some familiarity with VOAs, I would like to focus in the following case. So that's this theorem. By the way, I'm not completely sure about the author, like who came it up with first. I'm just going to point out that Dong came up with the representation theory of this side. I saw this theorem in Gano's book, and Simon Ledner, he was the one who pointed out for me. That states that if we have an even integral lattice and we denote the associated VOA as nu lambda, then there exists an equivalence of categories. So on the left hand, we have the category representations of this lattice VOA. And on the right, this should be equivalent to the category of vector spaces whose grading is given by this quotient. So this is like the dual lattice and the lattice itself. And the associativity is kind of tweaked, sort of saying, by a certain function I'm going to denote as omega. And you can come up what this guy is out of the lattice. So actually, this guy on the right is an example of something called point of fusion category. And algebra objects in these point of fusion categories were actually given by a certain theorem given by Ostrich and Natale back in 2003 and 2017, respectively. So our question here was the following: can we lift up this theorem here that classifies objects in this particular case of categories to a more general kind of category? In particular, we had one in mind, which is this group theoretical fusion categories in here. They were defined by Ettinghoff, Nishik, and Ostrich a while ago. And why we chose these guys is actually because they're an excellent ground, to test conjectures in fusion categories. So, if you have an idea, like, okay, if you want somewhere to try it out, these guys. And in addition, They are related to categories of representations of finite groups, which under certain constraints, you got group theoretical, semi-simple Hopf algebras, another kind, and so on. So, okay. We have this point of view. Oops, why did my cursor does this? We have point of view categories. We have a way of generalizing them. Actually, this result gives algebra objects in here. Can we lift it up into this, guys? So let's go. I wasn't particularly assuming that everybody is familiar with categories, so I thought about making a step-by-step introduction, and hopefully as comprehensible as possible. So I'm using the notation of this book by Ettinghoff, Gelaki, Nishik, and Ostrich. Any questions? Go there. Or if you're curious, go there. And let me start by defining what I mean by a monoidal category. So this consists of a tuple with a bunch of ingredients. C, this is going to be a certain category. A tensor product, which technically speaking, this is called a bifactor. So it's a functor between two copies of your category to your category itself. I'm going to need a special object in my category called unit. And then I'm going to need a certain family of natural transformations that go from, given three objects in my category, go from the tensor product of the first two and the third to the tensor product of the second and third and the first one. I'm going to call this family the associator. And finally, I'm going to need two more pieces. One is a natural isomorphism going from any unit tensor, any object in my category to the object itself, object tensor the unit into the object itself. So because I tensor on the left and on the right, I'm going to call this the left and right unita. And of course, I mean, all this structure doesn't come for free exactly. I mean, you need to check that everything is defined in a way that everything works well. So these are, I mean, two axioms, the pentagon and the unitar. Pentagon is like, take four elements in your category and in how many ways can you tensor them together so that the associator behaves as it should. A similar thing, I mean, to compare the structure of tensor, the tensor product and the units for the triangles. For simplicity, I'm going to use, I'm going to say simply C for the category. And easy examples of these, of monoidal categories, could be the following. The first one that comes to your mind, that can come to my mind, is the category of finite dimensional vector spaces, where my tensor product is given by the tensor product over my field K. The unit is going to be given by K itself. And well, I mean, you may remember from your linear algebra class, the associator, left and right unitar. I mean, this works. I mean, these are the obvious ones that you may be thinking of. But if you recall better your group theory class, well, we can always define the category of groups, where the direct product of groups is the tensor product. The unit is going to be the trivial group with just one element, and associator, left to right unitar, you can imagine which ones they are. All right, so if you give me two monoidal categories, how can I connect them? How can I relate them in a way that all this structure we're adding is actually preserved? This is the notion of monoidal functor. And if you give me two categories, that I'm going to call C and D, then, I mean, a monoidal functor is given by, first, a functor going from one category to the other, a way of relating their tensor products given by this family of natural transformations, so denoted fxx prime, going from the tensor product in the target category, going into the product inside the category, the first category, source category. And also a way of relating the units. So, I mean, first we have to relate the weight of, these two operations. Now we want to relate these two. And of course, there's some compatibility conditions here that need to be satisfied. So everything works well. So if you have an equivalence of categories, actually, in this case, you will have a monoidal equivalence. And well, this is, monoidal structure is like quite little. So we need, in order to go into fusion categories, into group theoretical fusion categories, we need to add many more ingredients. So I'll try to be as clear as possible. Before I start, let me fix K to be a field, algebraic clause, characteristic 0. I'm going to be imagining K to be C all the time, but yeah, I just wanted to be precise. So more structure, here we go. I'm going to call a category a tensor category, not monoidal, by the way. EGNO make this distinction, which is why I'm following this. We're going to say that C is a tensor category if, in addition to the monoidal structure you have, there is also some extra ingredients. To begin with, your homospaces, so every morphisms, the space of morphisms you can create between any two objects, this has a very nice structure. It has a structure of a k-vector space. So this is a k-vector space for any two objects. This is what is called, together with some other conditions, as k-linear. I'm going to be roughly speaking, so I just want to give you a slight idea of how this works and avoid technicalities. I'm going to request actually that these vector spaces, so in here, they're going to be finite dimensional. And this is what it's usually called locally finite. There's some extra technical constraints I don't want to go into. Then there is a notion of a kernel, a co-kernel, and there's short exact sequences. This is usually called abelian. My unit, remember the tensor unit, then we had in the monoidal structure, is actually a simple object. This means that you cannot actually break it in like smaller pieces. Or if this is like, okay, too much information, then you can take this, the equivalent condition that actually if you compute every endomorphism you can think of in your category, then this is actually equivalent to K, our base field. And then one last ingredient, rigidity. There exists a notion of a dual object, so more or less as you can think of in vector spaces. In the particular case of, I wrote here the case of a right dual. So if you have an object, you say, a right dual is another object in your category, and two maps called evaluation and co-evaluation map going between the tensor product of your dual and itself, or itself and the dual, onto the unit. And of course, they are subject to, certain compatibility constraints. So, in order to make everything work out well. Examples of tensor categories, well, let me just add another two simple ones to be, again, finite dimensional k-vector spaces. And also, if you include a certain G grading in your objects. Another easy one, the category representations of a finite group G over K, finite dimensional, another case of tensors. And hoping, that you could adjust all that, then let me define a fusion category as a tensor category that in addition has two more conditions. So it has finitely many simple objects, up to a certain equivalence. There's some extra constraints here. This is usually called finite, and semi-simplicity, which means that every object that you can have in your category can be written down as a direct sum of simple objects in C. Simple objects in C. Actually, the examples I just told you also work, and they are fusion. But actually, I would like to introduce quite an important one related to our original example. which is vec omega. I mean, this is the category of finite dimensional G-graded K-vector spaces, where the associativity constraint is actually governed by a 3 cycle that takes values, taking values in G, going into the non-zero field, elements of the field. Just to be more precise, if you denote the samples of your category as delta G's, and then, you can write down this associativity constraint. Remember, some object, and a morphism that goes from this product to this product. This can be written down as if you are going from the tensor product of these two first and the third one to the product, these two first and this one. This will be given by your 3 cycle times identity. By the way, the co-cycle has quite a lengthy constraint to satisfy. If you're curious, please ask. All right, so we have the definition of a fusion category. Let me remind for you a very interesting fact. The thing is that whenever we have a category that is fusion, and in addition is so-called pointed, that means that for the dual morphisms, the evaluation and co-evaluation maps, then we say C is pointed, and if you have a pointed fusion category, then it is automatically equivalent to this very special example introduced to you, vec G omega. So, which is actually kind of reduces the amount of fusion pointed categories that you can have. All right, remember that in the motivation of the talk, we wanted to generalize this theorem by Ostrich and Natali to this case of fusion categories, and we wanted to say, okay, which actually involves algebra objects in these pointed fusion categories. Just to be precise, let me tell you exactly what I mean by algebra object in this case. Tiny remark, if I'm gonna fix C to be fusion. Of course, almost everything that comes from now on, can be done in a much lighter setting, but just to save space and mental space. I'm gonna say that an algebra object in my category, or simply algebra, in C, this is a triple of one object in my category, a certain map, the multiplication map going between 2 copies of itself, the object itself, into A, and another object, another morphism that goes from the tensor unit to the object itself. And these need to satisfy associativity and unitarity constraints, as you will do in the case, for vectors, I'm defining just simple algebras. They, for example, look for the x per I, they look like something like this. But if not, just, of course, you cannot define any maps for free. There's some constraints to do. In this case, let me tell you a couple of examples of algebras. For the case of vec G, finite dimensional vector spaces with some G grading, an example of an algebra is a so-called group algebra, just given by KL when L is actually a subgroup of G. And in this very special case of vec G omega, it's actually going to be algebras are going to be given by very similar algebras to the group algebra, just that we need to tweak them a little bit. So how does this work? Well, these algebras are going to be given by summons. Graded over summons of these simple objects, one-dimensional vector spaces, and the labels are going to run through all the elements in your subgroup. In the multiplication, this is going to be given by the following. So this, which is a two-code chain, which is related, by the way, to the three-code cycle by this condition, which translates into this condition in here. And I mean, of course, this multiplication, landing into this object. These algebras, I mean, we're gonna, because of they're exactly, I mean, kind of tweaked, I mean, we're gonna call them twisted group algebra. And all right, I mean, we have pointed fusion categories, we have algebras. What comes next? And there is like one more ingredient I want to put into the equation, which is an equivalence relation for our algebras. So whenever you find a certain algebra object in your category, when can you say this is, I mean, that two different algebras are the same? Like, can you find a way of putting them all together in some equivalence class? And we do this by something called Morita equivalence. This is a notion originally introduced by Kitty Morita back in 1950. I mean, the motivation back then, it was a ring theory. So if you have two rings, let's say R and S, you're going to say that they are Morita equivalents if the category of modules of one is actually equivalent to the category of modules of the other one. But just, I mean, just saying, there's also similar relations, a similar definition in analysis, also in geometry. And in this case, I want to do something similar, but for the case of categories. So for this, I mean, in order to define this, I'm going to need some auxiliary notion, which is the notion of module category. Not the same as category of modules, not the same as modular tensor category. Fasten your seatbelts. All right, I'm going to define a left C module category to be an abelian. Remember, we had this Kernigel-Kernigel subsequences, K-linear, vector spaces, homospaces as K-vector spaces, semi-simple category. You can, you can write down every symbol in let's say, smaller pieces, equipped with a certain bifactor given by this. If you think of this like a module, I mean, but in a categorical, the definition of a module, but in a categorical way, this is more or less this. And some isomorphisms that relates actually, I mean, the tensor product inside this with the action on the module category. And of course, I mean, all these ingredients, again, need to satisfy certain compatibility conditions. So like the structure that you have in here, it's compatible. I mean, like everything you have defined is compatible with the structure inside of the category you're acting with on one side. Just saying, I mean, I'm defining this only for left, possible to define on the right. And nice examples of these categories, module categories, come actually from algebras. For this, let me define what I mean by a right A module. If you give me a certain object in your algebra, in your category being an algebra, I'm going to define a right A module in my category as a pair of an object in my category and a certain morphism going from my object, the algebra, into this. And of course, I mean, again, satisfying associativity and unitarity constraints. Analogously, you can define a similar thing for left modules and also for left and right modules. So, I mean, in this case, AB, where B is another algebra, by modules. If I put all these objects together in my category, well, let me denote this as CA for right A modules, and analogously for left A modules, and in this case will be AA by modules. And as I said, example, actually this guy here is an example of a left C module category, and you can prove that. I know this is a bit confusing, like that right is actually, I mean, a right my module is an, I mean, the right A module category is a left C module category. But I mean, actually it is true. And okay, once you have this, we can define what I mean by the notion of Morita equivalence. If you give me two algebras in my category, I'm going to say that they are Morita equivalent if this category of right A modules and for A and for B are equivalent using this left module category that I was defining in here. Okay, so almost there. Actually, using this Morita equivalence and module categories, you can say quite a lot. One with each other, and usually it's easier to work with algebras that represent Morita equivalence classes than with the module categories themselves, which is, maybe another reason to look for these guys. And as I said, using one and the other, you can tell about nice properties that they may have. So, for example, let me say, we can say that as an algebra objects, A in my category C is indecomposable and respectively semi-simple. If my category of right A modules, this guy in here, is again indecomposable, and the indecomposable respectively semi-simple of a category. And an example of these are actually our twisted group algebras in Vec G omega, in the case of Vec G omega. But actually, you're not constrained, to talk about algebra, properties of the algebra just by the category of modules or module categories. You can also just say, okay, these are some maps I can find within the with the algebra, and these properties hold because of this extra structure. And so we define the following. If we have an algebra object in C, then we say that A is a Arrhenius algebra if, in addition to the algebra structure, it also has the structure of a coalgebra. I haven't properly defined what a coalgebra is, but it's just the same definition as algebra, but reverse the arrows. So if you had the multiplication like this, then define a map like this on just on the other side to the on the other direction, and similarly for the unit. And so in addition, not only you have an algebra structure, you have a coalgebra structure, and in addition, these multiplication and co-multiplication and unit and co-unit morphism satisfies a certain compatibility condition. For the X bar I, in the graphical language, it will look like something like this. Once we have a Frobenius algebra, you can define something called special, very special. And this happens if two conditions, whenever you compose multiplication and co-multiplication, this gives identity. And a similar condition for the unit and the co-unit, just that you will not only have identity, you will have a certain element in your field acting in there. And finally, I'm going to be brief because I don't want to go too much into detail. I'm going to say that A is a separable algebra if there exists actually a kind of similar map to this co-multiplication I was mentioning before. If there exists a certain map, this should be a left module map and a right module map, and there's some extra conditions I'm skipping here. So quite a lot of adjectives up and down, but I hope now we are in shape to actually go to the main point, the main theorem of Ostertag-Natale and how we manage to generalize this. So Ostertag-Natale, here we go. It states that every Morita equivalence class of indecomposable semi-simple algebras in Vec G omega in my pointed fusion category, this is represented by a twisted group algebra. So remember this group algebra where the multiplication, it was kind of tweaked with this two cochain. And here, L again is a subgroup of G, two cochain, and which is kind of constrained to satisfy this condition with the 3 cycle. And our goal is to promote this result into the case of group theoretical fusion categories. And let's define it. What I mean by a group theoretical fusion category is actually a fusion category of the following form. So it's a category of, let's say, A, B modules. So where A, this algebra is given by this algebra in here. The tensor product is the product over these elements, this twisted group algebra. This is the monoidal unit given by the algebra, and it inherits the associator left and right unita from my back G omega category. Again, G is a finite group, K is a subgroup, 3 cocycle, cochain with constraints. And actually, this generalized the case of point of fusion categories because of the following. Because if we constrain ourselves to the case where this just doesn't exist, it's just taken trivially. So we take the group the trivial group, and we just take identity. This is actually monoidally equivalent to vec G omega. Similarly, if you keep forgetting more and more structure, then you will recover vec G. And I didn't write it down, but if you also forget the G, then you will get vec, the category of vector spaces. And another, it's whenever you say forget about the 3 cocycle and the cochain, the cochain, the 2 cochain, and take the same group, then you will land back into the category representations of this finite group. So first result, how did we do this? To generalize, I need to introduce one special ingredient. I'm going to take A to be a special Frobenius algebra. Remember, special had these 2 conditions for the unit and co-unit, and Frobenius algebra, co-algebra compatibility in a certain tensor category D. Then I am going to, you can prove that there is actually a certain monoidal functor. I'm going to denote this as phi, going from between the category D, my tensor category, into the category of AA bimodules in here. And how this acts on the object is as follows. So if you have an element X, you're going to tensor on the left and on the right with this A in here. In particular, this is, in a way, this is some kind of generalization of, let's say, the functor where we are thinking we're kind of after. Because if you take D to be vec G omega, then the target category is going to be our group theoretical fusion category, where we're taking again A to be this twisted group algebra. Okay, so we have a way of jumping between these 2. And this monoidal structure, it's actually quite nice because whenever you have an algebra in the source category, you will have an algebra in the target category. I actually didn't say exactly what this means. Having a Frobenius functor, this means for the experts that this is monoidal, comonoidal, and there's a certain compatibility condition going on. But let's say that that actually this functor allows you to not only go from algebra to algebra, it also allows you to go from Frobenius algebra to Frobenius algebra, which is like awesome. And then, okay, we had our twisted group algebras. Now let's use this functor and jump to the other category and see what algebra we find there. This is what we call the twisted Hecke algebra. and this is the Frobenius algebra given by the image under phi of our twisted group algebra. I'm going to denote this, with these, in order to try to make it slightly different to the twisted group algebras, I'm going to add some superscripts here. And actually, not only this Frobenius structure, going from algebra to algebra, he also preserve quite a nice lot of, algebraic properties in the, of these algebra objects. So let's compare what happens on each side. For the twisted group algebra, we have indecomposable, great, this is preserved. We have separable, which in addition is preserved. Frobenius, as I said, because we're using this, Frobenius functor, Frobenius monoidal functor. Specialty is also preserved, and there's like two more adjectives I would like to add. I haven't completely defined them, but okay, let's try to do it now. An algebra object is called connected if it satisfies this condition, that the dimension of the vector space. Wait, I wrote down something bad here, something wrong here. All right, this should be like the home space between these two. This is actually one-dimensional, so the unit morphism is unique, roughly speaking. And symmetric, this is roughly speaking saying that left and right duals, this is the right dual, if you remember from the definition. This is similar, the left dual, and this is an extra condition on the multiplication and the unit. And actually, so it was quite funny, that, all these properties were preserved, but actually being connected was not preserved. And something quite funny, you have that A is a symmetric algebra if you have a certain condition on your 3 cocycle. This cohomological function that kind of controls your associativity. And the thing is, whenever you want to have a look at what happens on the other side, this is absolutely not trivial at all to see, because this kind of relies on the internal structure of your group theoretical fusion category, like actually in particular of how, okay, how can I say this? It is absolutely not, not trivial to see, because it kind of goes back into the structure of the group theoretical fusion category, and you need setting, this category to satisfy a bunch of conditions that seems like it's not easy to see. So, and for this, well, that's what we're trying to work out, Moniki, Julia, and myself. Hopefully telling you soon why, a little bit more depth detail of this. All right, so, and then we arrive to our generalization of the Ostrick-Natali theorem. Remember that we had that every Moretti equivalence of class of indecomposable semisimple algebras in vec G omega was represented by twisted group algebras. We have a very similar thing, but in our case, for our group theoretical fusion category, these classes, they are represented by these twisted Hecke algebras, which was great. Because it's actually what you would expect. If you have some general, these group theoretical fusion categories, they are in a way a generalization. So whenever you constrain yourself, to the point of fusion category case, your twisted Hecke algebras actually go down into the twisted group algebras. Amazing. So just a word on how, this proof, how this works. This relied very strongly on some, a couple of facts. Well, to begin with, we needed to come up with the notion of a Morita preserving functor. Let me just go step by step. If you take two tensor categories, I'm going to denote them as C and D. and a tensor functor going from one to the other that satisfies two conditions. One, that it needs to preserve epimorphisms, and then this morphism relating the tensor product of one and the other needs to be an epi as well. So if you have two objects in your category C, I should have said here that they are objects in C. If these two are Morita equivalent, the thing is that this functor, tells you that when you're in the target category, they should be also Morita equivalent. And this is what we call Morita preserving. Okay, so this was actually important because if we wanted to go from to jump, we knew that in the source category in vecg omega, we knew that Morita equivalence classes, so we needed to go find something, a way, so that whenever we jump there, we didn't lose all the information, but we still kind of keep something. And then, well, in our particular case, if we take one tensor category and an algebra object in this category, two conditions again, special and Frobenius, then if we have two Morita equivalent algebras in my source category, then our functor phi, this functor that we defined to jump between our point of fusion category to group theoretical fusion category, and their images, they are also going to be equivalent algebras. And this actually, we managed to prove this in generality. But well, what we were actually looking for, it was, what this happened for the particular case of vecg omega in the point of fusion categories. Just saying that to prove this, actually, if you go from one direction to the other, this is what we just defined. We showed that our functor phi, it not only it's Frobenius, monoidal, but it's also Morita equivalent, Morita preserving. And the direction back, it was pretty tricky and took a lot of blood, sweat, tears in 4 continents together, but we managed, which is awesome. And okay, so I guess that's all the results I wanted to show to you. And what comes next? All right, just to let you know, the team is back, and we are working actually to generalize the results we came up with for this paper to a bigger class of fusion categories. Let me be baking here. And as I actually told you before, a subgroup of the gang is working on figuring out what happens. When can we have this symmetric twisted Hecke algebras? And as I said, this relies a lot on the structure of your category, and there's quite a lot to think about in there. So let's see. Let's hope we find some answers soon. Another question kind of related. This functor phi, if you think about it, it's really like the first idea it was literally the first idea we got. Okay, we will need to go from this category to the other category. Okay, just tensor with these algebra objects, done. So, and it was quite intuitive. So we were wondering, okay, wait a second. What is it unique? Can we do what other functors do we have there? Maybe we can find something, something more powerful, something more sophisticated that doesn't require as much work, especially in this part here. Yes, I'm traumatized. But so okay. Question. How many is there any more examples? Do they work? What about this functor? It was definitely too easy in that sense. And as part of my the PhD project of my students, Hannah, we would like to take all the techniques we use for this case of group theoretical fusion categories and import it to the case of modular tensor categories, and see if we can find a systematic way of go and compute examples of algebras in here. And actually, this is related to my question for you. I mean, how can we relate these results to the VOA case? I mentioned in the beginning, I mean, this example of the lattice VOA. One question I can think of, okay, do we have other examples of point diffusion categories? When does this happen? For example, I know that some colleagues that are working to prove that Heisenberg, for rank, at least for rank equals 1, this is also point diffusion, but which is kind of expected, from the lattice. But again, when does this happen? And when can we apply these results? Whenever we have another question, whenever we have a group theoretical fusion category, can we write this down as the category representations of some BOA? We're in the case of point diffusion. We have seen that we can reduce into the case of the lattice or maybe something else. What would it be? To get together, a group theoretical fusion category in this case. And the nice thing of, and the powerful thing of, this connection is actually that we can match VOAs, to other topics. For example, remember that in the beginning, I told you, okay, these group theoretical fusion categories, they are connected to representations of groups, to Hopf algebras. Well, this is a way of matching them together. Try to see, okay, if you have a question on one side, maybe you can solve it on the other, which is my last question here. And happy to hear about your ideas. And I think that's it for today. Thank you very much. I think it was super quick.
Thank you, Anna. Thank you so much. Let me stop the recording and